I'm Cassandra Mercury. I am the Quantum Space Technologies Lead at Craft Prospect, and we're going to be going over quantum key distribution and specifically from space. But we'll be doing quite a bit of background on what quantum key distribution is first. Let's see. There we go. So I went to the University of Southern California, had my degrees in astronautical engineering. Straight from there, I went to JPL, you can see on the left. I worked on the Mars Curiosity rover and some other extraterrestrial enabling technologies. I left there, went to a high-tech startup doing a new type of transportation called the Hyperloop. And then now I'm in Edinburgh in Scotland, and I am working on the UK's first quantum key distribution payload that's going to be launching in 2022. So first, in getting into quantum key distribution, it's why you need it. It's a type of encryption. And you need encryption because you need to protect your high value data. That data is everything from financial to privacy considerations with your health data, as well as with corporate assets. So for example, natural resource mapping in the North Sea, any company that invests in that is going to want to keep that secure because they've put a lot of capital into it. So you need to be able to securely store as well as transmit this data. So you need to protect your assets and your finances, your privacy, and to protect any competitive advantage you have in industry. And so to do that, you encrypt your data. So what's the issue right now is that we have lots of encryption methods and they all work quite well for current times. The most popular one is the RSA one, and what that relies on is how hard it is for computers to be able to crack really complex math problems, and in particularly to factorize large prime numbers. So as you can see from the chart on the left, as the number of bits increases, so as those prime numbers get larger and larger, it becomes harder and harder. It takes longer to brute force an attack and be able to crack that factorization of what numbers went into it for any at least classical algorithm. For the RSA, for a 2048-bit encrypted key, it would take about 300 trillion years to crack into it. So obviously that's basically computationally secure for now. The problem comes in is when you start having quantum computers. So quantum computers use qubits instead of bits. And those qubits allow you to introduce probability into your calculations, and it makes things a lot more efficient. So there was a mathematician named Peter Shor, and so he created the Shor algorithm for use by a quantum computer. And what you can see is that the larger the number of bits, the runtime to be able to crack that doesn't get really significantly larger. So once quantum computers come on, factorization becomes quite easy. Like how easy? Well, the current estimate is that having a quantum computer with 4,099 qubits would allow you to break that 2048-bit encryption key encrypted with RSA in about 10 seconds. So obviously that leaves a lot of data very vulnerable. Now we're not there yet. IBM currently has, I believe, 53 qubits on their computer. And Google has created one, the bristlecone, that has 72 qubits. And they're not perfectly stable at the moment. So they still don't meet the requirements to be able to break into these encryption. But right now, what we're looking at is about 10 years for quantum computing to come online and to be able to do this encryption breaking. Now, that's not only a problem for the future when we have quantum computing, but it's for any data that you still want to be secured in 10 years, because you can save all of that data, encrypted data, and just wait until you have a quantum computer that can break it. So if there's data that needs to be secure for longer than 10 years, that's a problem that needs to be looked at now. And so that's what leads to quantum key distribution, where the quantum keys are what's going to encrypt your data. So you get the secure keys. It's provably safe against quantum attacks by quantum computers. So even with the coming advent of quantum computers, it won't be able to be broken into. And it's part of a full cybersecurity toolbox where you still have to think about, access to the electronics, transmission points, and all the regular things that you think of when you're securing any computing system. And then those keys are able to be used for basically anything we use current keys to encrypt. So that's, all your finances, that's your privacy data, that's network security, that's any of your natural resource assets. Basically, you use it just as you use any current encryption methods. So that gets into what is quantum key distribution and how does it work? Well, you start off with Alice. Alice is your transmitter, and Alice wants to be able to communicate with Bob securely. So what Alice does is Alice sends encoded photons. So these photons are encoded with information, and they do that by polarization states. There's a couple of ways to do QKD, but this is the method that we're going to be using, so I'm going to speak to that one. So polarizations, are what you're seeing there, or vertical, horizontal, diagonal, anti-diagonal. And then Alice has a quantum random number generator to randomly select which of those photons get sent at any one time. So Alice sends a large number of photons to Bob randomly. Bob has the receiving equipment to decode what the photon state is. And then they develop the raw key. Then there's a lot of stuff on the back end that happens in the reconciliation process to create a secret key. And that secret key is the encrypted quantum key. The secret key is needed because you might have basically an eavesdropper. So there's a bug in the middle of your quantum channel that's trying to determine what that key is, because getting that encrypted information will open up a lot of data for any bad actor. So anything you want to encrypt, there's probably somebody that wants to decrypt it. So how do we protect? How does quantum key distribution protect against this eavesdropper, this bug in the system? Well, it's basically through the principles of quantum mechanics. There's something called a no cloning theorem, and you can't alter the state of the photon. And by trying to measure it, you're changing it. So Alice and Bob, during that back-end process I was talking about, they'll be able to detect if there was a bug in the system trying to eavesdrop, because an error rate will increase, and they'll be able to discard that key knowing that it was eavesdropped on. And so no encrypted data will actually get exchanged. So that protects it. And then once Alice and Bob are actually able to send a key without an eavesdropper in there, they're able to then create what's called a one-time pad. And that allows them to securely transmit messages over any public channel. So it doesn't need to be a secure encrypted channel. You just need a secure encrypted key. So just like you use with any sort of encrypted messaging services that you use now, you have the private key and then you use the public channel. And so once that one-time pad is used up, you have to create a new key. So it's used once to securely send over all your information. So now that's what QKD is, but why do you want it on a satellite? Well, there's a couple of reasons. One is that terrestrial networks have really large losses. So you do have fiber-based QKD, and that's a shown process. But there's a lot of losses and attenuation due to that fiber. So you don't really get a large amount of bit rates. So your keys are very small, it takes a long time, and the error rates really go high. Now you can have repeaters in there, but there's only so long that it can increase your range. Right now, really a maximum and at a really slow bit rate is about 100 kilometers. And the distance from where I am in Edinburgh to Leeds is over 3 times that. So fiber-based QKD is really good for local areas, local networks. There's other there's basically free space QKD, where you have 2 places on Earth. The problem there is that you have to have line of sight. So you have to, Alice and Bob have to be able to see each other to send those encrypted photons. And there's attenuation due to the Earth's atmosphere. So you get a lot of losses, so it's not very efficient. So it basically means that the distance for free space QKD is about 500 kilometers. So that's why we're looking at QKD on satellites, because once you're up in space, you have a much larger range. You can have Alice and Bob basically be able to be located anywhere and be able to send encrypted keys between them so that they can then be able, any two areas, any two receivers can then talk to each other securely. And so that gives you a lot more distance. It prevents you from having to have a lot of ground infrastructure with laying all that fiber and having the repeaters. And so we're up at about 500 to 600 kilometers is what we're looking at for our mission. So that's very low Earth orbit. You're still going through the atmosphere, so you're still having some of those losses through, atmospheric losses in your signal, but it's much less. Now, there's a couple of ways that you can do QKD on satellites. You can have the transmitter on board the satellite, or you can have the transmitter on the ground. Both of them have their trade-offs, whether you're going through the atmosphere first or later. That really increases or decreases what your losses are, but there's other trade-offs from it. Now, the mission I'm working on is going to have our quantum source up on top in that satellite, going to a receiver on the ground. So there's quite a few satellite missions for QKD. It really all kicked off in 2016 when the Messias satellite from China went up, and they were able to show that they could do QKD and have a video conference between China and Austria on a secure channel. So that really kicked off a lot of other countries wanting to get that same sort of capability. And so a lot of funding started going through it. Now, that satellite was a very large satellite. It was 631 kilograms. A lot of the missions that are upcoming are much smaller. So they're much smaller demonstration ones to be a bit more agile to be able to prove it. Now, the Chinese Messias satellite used entangled photons. And there's going to be one with RAL Space. It's a joint UK-Singapore mission. They're going to be doing entangled photon sources on board, and they're doing a small satellite. There's one in Canada called KeySat, and they're going to be doing an entangled source, but they're going to be doing it on the ground with the receiver being on the satellite, and they're also a small sat. And then the project that I'm working on is called ROCS. It's for responsive operations on key services. And so our aim is to be the first UK one that goes in 2022. And we're going to be having our transmitter on board the satellite, and we're going to be using what's called the WCP protocol. So it's the weak coherent laser pulse. So it's a different type of QKD. Trying to get into all the different types of QKD. I'm sorry, it's a really interesting subject, but it can get complicated. But one of the things we're doing is we're using a 6U CubeSat to be able to do that. So these much smaller, like their max weight, mass is 12 kilograms. So a lot smaller than the Messias one. And so for a CubeSat, their basically dimensions are given in terms of U, where 1U is 10 by 10 by 10 centimeters of space. And there have been CubeSats that are just 1U that get sent out, but you can also, they're modular, so you can add more. So 2U is, 10 by 10 by 20 centimeters, 3U, 6U, they go side by side. And that's what we're going to be doing for our ROCS QKD mission. And you can also have larger ones where it's a 12U, where it's 2 6U kind of next to each other. And just to make sure that the scale here, a 6U is only 30 centimeters tall. So that's basically to scale a, rather large loaf of bread, but a loaf of bread. So these are smaller, so you're able to be a lot more agile, try out things a lot quicker to be able to prove your concepts pretty quickly. So that's what we're excited about. So this is basically the satellite bus for a 6U CubeSat, and that's what we're going to be using. About half of that space is for the QKD payload, where you have a large telescope at the front. And so we're actually using a 90mm aperture And then you have the optics and the transmitter in there. Didn't have quite enough time to fully show how everything works there all together. But if you have questions, you can send them to me and I can, give you a bit more information on the ROC's mission. But yeah, so that's basically how QKD works, and the upcoming missions that we have to demonstrate QKD from space.